Hello everyone. In the previous topic on interrupts, we have studied the introduction of CPU interrupts. We learned that the interrupt is a mechanism which changes the flow of control. The transfer of the program control takes place either by the occurrence of an event internal to the processor hardware or an event in its external hardware. Today, we are going to study various types of hardware interrupts along with the various applications of the interrupts. Also, the design issues related to handling multiple devices using limited interrupt signals on the CPU, as well as resolving conflicts when multiple devices simultaneously try to send interrupt signal are explained in brief. In the earlier topic, we have studied interrupts classified under 5 groups as hardware, software, internal, non-maskable interrupt and reset. The hardware interrupts are further classified into 3 categories as 1. Level triggered, 2. Edge triggered and 3. Hybrid configuration. First, a level triggered interrupt is an interrupt signaled by maintaining the interrupt line at a high or low level. A device willing to signal a level triggered interrupt drives the interrupt request line to its active level high or low and then holds it at that level until it is serviced. It ceases asserting the line when the CPU commands it to or otherwise handles the condition that caused it to signal the interrupt. Second, an edge triggered interrupt is an interrupt signaled by a level transition on the interrupt line, either a falling edge, that means momentary high to low and then high again, or a rising edge, momentary low to high and then low again. A device willing to signal an interrupt drives a pulse onto the line and then releases the line to its inactive state. The third type of hardware interrupt is hybrid configuration. Some systems use a hybrid of level triggered and edge triggered signaling. The hardware not only looks for an edge, but it also verifies that the interrupt signal stays active for a certain period of time. The hybrid signal is useful for non-maskable interrupts input signal called NMI in short. The NMIs generally signal major or even catastrophic system events. In order to avoid spurious interrupts, a good implementation of the NMI signal tries to ensure that the interrupt is valid by verifying that it remains active for a certain period of time. Next, various design issues related to interrupt handling are explained. Due to the limitations of the integrated circuit chip design, limited pins, maybe 1 or 2 pins, are reserved for receiving interrupt signals from the hardware devices. However, the design issue is how to connect multiple external hardware devices so that they can raise their interrupt signals on one of the available interrupt pins on the CPU chip. Also, the important design issue is how the CPU can detect which device has interrupted. The second design issue is to decide the priority of various connected devices. The priority assigned to every external device is useful when more than one device simultaneously interrupts the CPU. The CPU first handles the higher priority device using the arbitration logic either present inside the CPU or through an additional hardware attached to the CPU. So, the important design issues can be summarized as 1. There are multiple I/O modules. How does the processor determine which device issued the interrupt? Second, if the multiple interrupts have occurred, how the processor decides which interrupt out of the multiple interrupts is to be processed. There are 4 common techniques which are used for the device identification. The first technique is multiple interrupt lines. Second technique is software polling. The third technique is daisy chaining. It is also called hardware poll vector. Fourth is bus arbitration. First, starting with the first we have multiple interrupt lines. The most straightforward approach is to provide multiple interrupt lines between the processor and the I/O modules. However, it is impractical to dedicate more than a few bus lines or the processor pins to the interrupt lines. Therefore, multiple devices are connected over limited interrupt pins. In the Intel family of processors like 8088, 8086, 80286 and 80386, only one pin called INTR pin is used for interrupt signaling, and a single interrupt acknowledge signal is available called INTA in short. Therefore, to allow the multiple devices with different priorities to interrupt the CPU, an external hardware called interrupt arbiter is used. The 8259 interrupt controller is one of the integrated circuit chip which receives interrupt from the multiple external devices, resolves priority and conflicts, and generates a single interrupt signal to the CPU through the INTR pin. A single 8259 interrupt controller can handle up to 8 external devices. If the control for more than 8 devices is required, a hierarchical arrangement of 8259 integrated circuit chips may be used to handle up to 64 external devices. When the interrupt controller generates the interrupt signal over INTR pin, the processor responds by generating an interrupt acknowledge signal. The interrupt controller then places the appropriate vector information on the data bus. The information so received helps the CPU to process the interrupt by transferring the program control to the interrupt service routine corresponding to the device raising the interrupt. The interrupt controller provides 3 modes of operation. First mode of operation is fully nested. In a fully nested mode, the fixed priorities are assigned to the 8 devices from 0 to 7. In a rotating mode, which is the second mode of operation, all the interrupt devices are assigned equal priority, and therefore, a device being serviced once is assigned the lowest priority in the group. In the third mode, called special mask mode, it is possible to mask some of the interrupting devices by setting flags in the command status register of 8259. The setting of the above 3 modes, including setting of the flags, is done using the software written in the CPU, and therefore, 8259 interrupt controller is also called programmable interrupt controller. The next design technique is the software polling. When the processor detects an interrupt, it branches to an interrupt service routine whose job is to poll each I/O module to determine which module caused the interrupt. The poll could be implemented with the help of a separate command line, that is test I/O. In this case, the processor raises the test I/O and places the address of the particular I/O module on the address lines. The I/O module responds positively if that module has raised the interrupt. Alternately, each I/O module could place an address of its corresponding interrupt service routine called ISR in short on the data bus, so that CPU can receive the address and transfer the program control to its corresponding interrupt service routine. The main disadvantage of the software poll is that it is time consuming and therefore is not preferred in real time applications, which require immediate response after the occurrence of the interrupts. The next design technique is daisy chaining. It is a wiring scheme in which the multiple devices are wired together in a sequence or in a ring. In this method, all I/O modules share a common interrupt request line for sending interrupt to the CPU. However, the interrupt acknowledge line is connected in a daisy chain, sends out an interrupt acknowledge. The interrupt acknowledge signal propagates through a series of I/O module until it gets to a requesting module. The I/O modules are connected in the order of their priority. The higher priority device gets preference over the lower priority device to respond to the interrupt acknowledge signal. The requesting module typically responds by placing a word on the data lines. This word is used as a unique device identifier, which can be used to direct the program control to the ISR corresponding to this device. In some implementations, the device identification number is directly mapped to the address of the appropriate interrupt service routine for that device. This technique is also referred to as a vectored interrupt. The next design technique is bus arbitration. In the bus arbitration method, an I/O module willing to communicate with CPU must first gain control of the bus before it can raise the interrupt request line. Thus, only one module can raise the interrupt line at a time. When the processor detects the interrupt, it responds on the interrupt acknowledge line. The requesting module then places its vector on the data bus. The next design issue is how to handle multiple interrupts. When there are n I/O modules connected to n interrupts provided on the CPU chip, the process of identifying the requesting I/O module is simple and straightforward. However, when there are many I/O modules connected over the limited interrupt pins, the techniques are needed to identify the requesting I/O module. There are several techniques to identify the requesting I/O module. These techniques also provide a way of assigning priorities when more than one device is requesting interrupt service. With multiple lines, the processor just picks the interrupt line with the highest priority. During the processor design phase itself, the priorities may be assigned to each interrupt lines. With software polling, the order in which the modules are polled determine their priority. In case of daisy chain configuration, the priority of the module is determined by the position of the module in the daisy chain. The module nearer to the CPU gets the first priority in the daisy chaining, because this is the first module to receive the acknowledged signal that is generated by the processor. In case of bus arbitration method, more than one module may need control of the bus. Since only one module at a time can successfully transmit over the bus, some method of arbitration is needed. The various methods can be classified into two groups, centralized and distributed. In a centralized scheme, a single hardware device referred to as a bus controller or arbiter is responsible for allocating time on the bus. The device may be a separate module or part of the processor. Any device willing to take control of the bus is required to make request to the bus controller. The bus controller, depending upon the priority of the device, assigns the control of the bus to the requesting device. In the distributed scheme, there is no central controller. Rather, each module contains access control logic. For example, there are as many request lines on the bus as devices. Each device monitors each request line after each bus cycle. Each device knows if it is the highest priority device which requested the bus. If the device making the request has the highest priority, it takes the control of the bus without any central arbiter assigning bus control to the device. With decentralized arbitration, no arbiter but more bus lines are required. Next, the typical uses of the interrupt are explained. One of the important uses of the interrupt is to communicate with external devices which are slower as compared to CPU. The interrupt driven communication eliminates the waiting or polling by CPU for data from external devices. The typical task of any device performing input and output are: first is control, second is test, third is read, fourth is write. These tasks are provided through I/O commands. The control commands are used to activate a peripheral and tell it what to do. For example, a pen drive may be issued a command to lock or unlock for any read or write operation. The control commands are specific to the type of the device the CPU is communicating with. The test commands are used for testing various conditions associated with an I/O module and its peripherals. For example, a command may be issued to test whether the device is powered on or not. For example, in a printer device, we can issue a test command to test if any error occurred in the previous print operation like paper jam, no paper or hardware fault. In case of disk operation, we can check if the disk write operation was successful and parity checks revealed the correctness of the write operation. The third set of commands is for reading data from the device. The processor issues a read request and the device responds by placing the requested data on the database. The write command causes a byte or word to be returned to the device from the processor memory. Both the read or write operation from the CPU to I/O module or I/O module to CPU is either 8 bits, 16 bits or 32 bits. The unit of data transfer depends upon the width of the data bus and the capability of the device and the available parallel interfaces. In case of serial communication, the unit of the data transfer from CPU to I/O module is a single bit at a time and is measured in baud rate. Using these commands, now let us understand how an interrupt driven I/O is performed. For input, the processor issues a read command. The processor knows that the device is slower and may take its own time to deliver data. Meanwhile, it switches to some other program instead of waiting for the device. When the device is ready to deliver data, it sends an interrupt signal to the CPU. The CPU finishes the current instruction and saves the current value of program counter, program status word and registers and stores them in the memory. The program control is then transferred to the interrupt service routine. The ISR reads data from the device and saves it in memory. It then restores the context of the program it was working on and resumes execution. The sequence of the I/O operations can be summarized next. The device issues an interrupt signal to the processor. Second, the processor finishes the execution of the current instruction before responding to the interrupt. The processor checks for the interrupt. If it occurs, it sends an interrupt acknowledge signal to the device sending the interrupt. The processor now saves its current status, value of program counter and other registers in the memory and transfer the program control to the interrupt service routine corresponding to that device. When the ISR completes the read operation, the saved register values are restored from the memory. As a result, the next instruction to be executed is from previously interrupted program. Another use of interrupt is for implementation of system timers. The timer as a device is capable of sending interrupt to the CPU after every predefined time interval. The CPU can then perform timer related activities at regular intervals without polling the timer again and again. For example, if a timer is configured to send an interrupt signal every 2 seconds, the CPU after receiving the interrupt checks the status of all devices connected and updates their status on the monitor. During these 2 seconds, the CPU can perform other activities in the system. Another use of interrupt is to detect the power off signal and interrupt the device. These interrupts are given highest priority by the CPU. When the CPU receives the power off signal, it responds by switching to an alternate power supply like batteries. One typical use is to generate interrupts periodically by dividing the output of a crystal oscillator and having an interrupt handler count the interrupts in order to keep time. These periodic interrupts are used by the operating system to maintain the current time and date. These systems are made operational with the help of a small battery and works even during the time when the system is powered off. So, what we have learned today can be summarized as what is an interrupt, what are the types of interrupts, typical uses of interrupts, and various design issues related to handling multiple devices over limited interrupt pins. Also, the issues related to priority of devices were explained in brief. Thank you.